class, I want to cover the last section in our class 5.5, the substitution rule. And you'll go over this again in Calc 2. It's very, very important in Calc 2. You use substitution, all the time in the class. So, substitution, if you think about integration undoes differentiation, and substitution undoes differentiation that uses the chain rule. Okay, so if you integrate, this is the outside function evaluated at the inside function times the derivative of the inside function. Well, then the antiderivative of that is going to be the outside function evaluated at the inside function plus c. And that's because by the chain rule, if you differentiate this composite function, you get the outside function evaluated at the inside function times the inside function, the derivative of the inside function. So you see, you're integrating this, so you get back what was differentiated. So you can write it in a little different notation. Let u equal g of x, then du dx is g prime x, then du is g prime x dx. So the way the substitution rule works, if u is equal to g of x, if it's a differentiable function whose range is an interval I and f is continuous on I, little f is continuous on I, then the integral of this composite function times the derivative of the inside equals, and we're just kind of rewriting it in another notation, f of u, and then the g prime x from up here is du. So we're just making a substitution and making it easier to integrate. So this is what we have to do a lot of the time when we're doing integration in Calc 2. So say I want to integrate this function. Well, the trick is figuring out what to let u be, and it's a bit of an art. It takes practice, but a lot of times we let u be the inside of a composite function. So if you notice right here, I have a composite function, and if I let u, well, let's look at the composite first. G of x would be the inside function, and it's 2 plus x to the 4th. The outside function, f of x, would be x to the 5th. So if you do the composite of f of g of x, you take the inside and you put it into the outside. So this is a composite function. So let's let u be the inside function, so let u be 2 plus x to the 4th. Then you need to find the derivative of that. That's going to be 4x cubed. And then I just cross multiply here to say that du is 4x cubed dx. Now, I'm going to look at my integral again, and I'm going to just reorder it a little bit. I'm going to write an x cubed over here. Now, what I need, I want this whole thing to be du. And it's x cubed. There was an x cubed, but I need a 4. I can multiply by a 4 as long as I divide by a 4. And then I can make the substitution. This is exactly du, and since u was 2 plus x to the 4th, this is u to the 5th. Well, now that's easy to find the antiderivative for. It's going to be the u to the 6 over 6, because remember, we add 1 to the exponent and divide by the new exponent plus c. And then we've got to multiply times the 1/4. And so now I don't want to leave my answer like this. The variable that we started with was x. And so my answer needs to be in terms of x. So my substitution was u equal 2 plus x to the 4th. So if I just rewrite 2 plus x to the 4th, where u is, and then you can, multiply that and get 1 over 24. Now you can always check integration by differentiation. So I'm going to differentiate this. So I'm going to bring down the 6, and I'm going to subtract 1 from the exponent, and I'm going to use the chain rule and multiply times the inside. And then I just kind of simplify that. And so that's going to give me 2 plus x to the fourth raised to the fifth times x cubed. And that is what we started with. Okay? So that's substitution. Okay, the idea behind the substitution rule is to replace a relatively complicated integral by a simpler integral. This is accomplished by changing from the original variable x to a new variable u that is a function of x. The main challenge in using the substitution rule is to think of an appropriate substitution. You should try to choose u to be some function in the integrand whose differential also occurs except for a constant factor. If that is not possible, try choosing u to be some complicated part of the integrand, perhaps the inner function in a composite function. Finding the right substitution is a bit of an art. It's not unusual to guess wrong. If your first guess doesn't work, try another substitution. Yes, because you should be able to tell whether it's going to work or not. And if it doesn't work, then that means you haven't chosen the correct, probably means you haven't chosen the correct substitution. So, yeah, a lot of times, not always, we choose u to be the inside function of a composite function. But remember that whatever we have, like if we choose u to be the inside of a composite, the derivative of u must also be a factor in the integram. So here's another example. Okay, so we want to integrate this function. Now, we have a composite function. This is a composite secant squared 1 over x, and you can see that the inside is 1 over x, and the outside is secant squared x. Excuse me, I'm losing my voice. So let's try letting u be the inside function. So if we let u be 1 over x, the derivative of u would be, because you know this is x to the negative 1, it would be negative 1 over x squared, and if I do my little cross multiplication here, my du will be negative 1 over x squared dx. Well, now look, I have a 1 over x squared in the integrand, so I just need to multiply by a negative. So let's see how that's going to look. Okay, I want this to be exactly this. So I'm going to multiply by a negative, but that means I have to also multiply by a negative on the outside. Or you can think of it multiplying by a negative 1, dividing by a negative 1. Then this, because I'm going to let u be 1 over x, this is secant squared u, and this is du. Well, if I rewrite it like that, I can find the antiderivative, because the antiderivative of secant squared u is tangent u plus c, and then I've got the minus sign. Then I reverse the substitution because u is 1 over x, so I have minus tangent of 1 over x plus c. And you could check it. The derivative of my answer would be secant squared, or minus secant squared 1 over x times the derivative of 1 over x. And this simplifies into this, which is what I started with. So that works. Here is a classic substitution problem. You can see that I've got a composite. Let u be the inside. The derivative would be 3x squared. So my du would be 3x squared dx. And I've got an x squared. I just need to multiply that by 3. So I just grouped it over here. I multiply by 3. I divide by 3. Then this is my u to the 10th, and this is my du. And of course I got 1/3. And then I have 1/3 u to the 10th times du. The antiderivative, I add 1 to the exponent, divide by the new exponent, and then I want to reverse the substitution. So where I have u, I want to write x cubed plus 5. And there is my answer. I won't check this one, but it should check. Now this one's a little bit different because I'm going to let u be the inside function, but then my du dx is just a 1, and so du equals dx. But I've got this x here that I need to do something with, because remember, you need to have everything in terms of u. So you need to change everything to be in terms of u. So I've got to change this x to be in terms of u. But if u is equal to x minus 4, then x is equal to u plus 4. So I can change this x to u plus 4. So I do right here. And then I've got the square root of u. Now, what this has done, it's given me one term under the square root, and I can write that as u to the 1/2, and I can distribute. I couldn't do that here. So I distribute, and I get u to the 3/2 plus 4u to the 1/2. Then I can find the antiderivative of that. Add 1 to the exponent, divide by the new exponent, add 1 to the exponent, divide by the new exponent, and go plus c. And then I simplify that, and that's my, well, that's not my answer. I have to reverse the substitution. So I replace u with the x minus 4, and then I have my answer, and you can check it. You can go through and check it. Another example, I've got the sine of square root of x over square root of x. I've got a composite. Let u be the square root of x, which is x to the 1/2. The derivative of that would be 1/2 x to the minus 1/2. And so my du, can just rewrite that in another form, 1 over 2 times square root of x. So du then, if I cross multiply, will be 1 over 2 times the square root of x dx. I've almost got that. I've got a 1 over the square root of x dx. I just need to divide by 2 here, and I can do that if I multiply by 2. So that's what I'm going to do, because I want this to be this. It didn't have that 2 in the denominator, so when I put that there, I'm dividing by 2, so then I need to multiply by 2, so that I really haven't changed the problem. Then I'm going to write everything in terms of u, and so I have a much simpler integral. The antiderivative of sine of u is a minus cosine u, so my answer so far is minus 2 cosine u plus c. But then I've got to reverse the substitution. U was the square root of x, so I have minus 2 cosine square root of x plus c. Okay, sometimes, really a lot of times, you have to rewrite things so you can see what you want to use for the for the substitution. Well, I just wrote the 1 over 1 plus tangent t, and then I wrote times 1 over cosine squared t. But 1 over cosine squared t is just secant squared t, and now I see there is a relationship between tangent t and secant squared t. Now, this is actually a composite right here. It's like 1 plus tan t to the negative 1. So, when you let u be 1 plus tangent t, you are really letting it be the inside of a composite. Now, my derivative of u would be secant squared t. So if I cross multiply, du equals secant squared t dt, and I've got that right there. Okay, so all I've got to do is write it in terms of u. So I have 1 over u du. The antiderivative of that would be natural log of the absolute value of u plus c. And then I need to reverse the substitution. So u is 1 plus tangent t. So I reverse it. And then you could go and check it. If you do the derivative of this, it's going to be 1 over 1 plus tangent t times the derivative of the inside, so times the secant squared t, which is the same thing as what we started with. This is kind of another classic integration substitution problem. So I look at this and I see, hey, if I let u be z cubed plus 1, the derivative of that's going to be 2z squared. Now I do need to let u be z cubed plus 1 and not just z cubed. So I'm going to let u be z cubed plus 1, and I don't know, I just rewrote it over here, but then the derivative of that would be 3z squared, and cross multiplying du would be 3z squared dz. Well, I've got a z squared, I just need to multiply by 3 and divide by 3, and then I can write everything in terms of u, and this is just du. It's the same thing. and the antiderivative of 1 over u is natural log of the absolute value of u. And I've got the 1/3, and I go plus c, and then I just reverse my substitution, and that's it. Okay, another example, and this is one where I need to play around with it a little bit, and I think there's more than one way to do this one, but one way to do it, let's just write out what we have. Cosecant x is 1 over sine x, so this is 1 over sine cubed x, and cotangent x is cosine x over sine x. So I have a cosine x over sine to the 4th x. So what I could do is let u be sine x, then my du will be cosine x, and so my du will be cosine x dx, and I have a cosine x dx, so I just need to rewrite it in terms of u. This is 1 over u to the 4th, and this is du. And I can find the antiderivative of that. I just add 1 to the exponent, divide by the new exponent, and then I need to reverse the substitution, and that's it. Now this one is a little bit different because if I just let u be the denominator, the derivative of that is going to be 4x cubed. And I don't have a 4x cubed, I have an x. And you can't just go multiply by x squared. You can multiply by a constant, but you can't multiply by x or divide by x. You can't do that. So if I think about it, my x to the 4th is x squared squared. So if I let u be x squared, then my du dx is 2x. The reason I wanted to do that is because of this x. I need to somehow turn that into the du. So my du is 2x dx. So that x that was up there, if I just multiply it by 2, it's my du, and then I've got to divide by 2. And then I have the 1 over 1 plus x squared squared. Well, now, if I'm letting x squared be u, this is 1 over 1 plus u squared, and this is my du. So the antiderivative of that is tan inverse of u, and then plus c. And then I reverse it because u is x squared, and then of course you can check it, and it will check. Now, we also use the substitution rule for definite integrals. So if g prime is continuous on the closed interval a to b, and f is continuous on the range of u equals g of x, then the definite integral, and you've got f of g of x times g prime x, you need to change the endpoints to be in terms of u. So you go g of a, g of b, f of u du. And I'll explain what I mean by that. So here we're going to evaluate a definite integral, and this is what I have. This is a composite function. This is sine of sine x. So I'm going to let u be sine x, that's the inside function, and the du dx would be cosine x. So my du is cosine x dx. So I've got this, sine of u, because u is sine x, and I've got the du cosine x dx. Just reorder things. But I need to change these endpoints. So if u is equal to sine x, then when x equals 0, u is equal to sine of 0, which is 0. And when x is pi over 2, u is equal to sine of pi over 2, which is 1. So then instead of 0 and pi over 2, I'm going to use 0 and 1 for my endpoints. And then I find the antiderivative of sine u, which is negative cosine u, and then I evaluate, and I get cosine of 0 is 1. This is my exact answer. Now what I did here, I didn't have to reverse the substitution. I just changed the endpoints to be in terms of u, and then I went ahead and evaluated. Now your other option is that when you get to this point, you could reverse the substitution and use the original endpoints. you'll get the same answer. Same answer. So, I'll probably recommend changing the endpoints and getting everything in terms of U. But to tell you the truth, and then you don't have to reverse. Um, to tell you the truth, it doesn't really matter. And now be careful. If you change the endpoints, you don't want to reverse. It would be wrong to reverse the substitution. If you don't change the endpoints, then you need to reverse and use the original endpoints. So either one of those will work. Okay, I've got another definite integral. I notice there's a tan x, and there's a relationship between tan x and secant squared x. Tan x is the inside function of e to the tan x. So the inside function's tan x, and its derivative is secant squared x. So that's going to work if I let u be tan x. Then my du dx is secant squared x, and du is secant squared x dx. So this is going to be e to the u, and this is going to be du, but I need to do something about those endpoints. So I decided just to go ahead and change them. So when x is 0, u would be equal to, because u is tangent of x, so u would be tangent of 0, which is 0. When x is pi over 3, u would be equal to the tangent of pi over 3, which is the square root of 3. So these are the new endpoints right here. And then this is EU du, and then I've got endpoint 0 square root of 3. The antiderivative of e to the u is e to the u. And then I evaluate at the endpoints. E to the 0 is 1. And so that's my exact answer. I also could have, at this point, reverse the substitution and use the original endpoints. Okay, another theorem. The integrals of symmetric functions. Suppose f is continuous on the interval from minus negative a to a. So this is a symmetric interval. If f is even, which means that when you put in a negative x into f, you get back the same thing, then when you integrate over a symmetric integral, you get twice what you would have gotten if you integrated from 0 to a. Now, if f is odd, so that means when you put in the negative x, you get back the opposite of f of x. Then when you integrate over a symmetric integral, you get 0. So this is an even function. And so when I integrate an even function over an even integral, I just get twice this area. But this is an odd function. So when I integrate over a symmetric interval, this cancels out with this, and I get 0. So here's an example of that. So I notice that my interval is symmetric. And then really what I want to figure out is this an even or an odd function. We don't know how to integrate this right now. So the only thing we could do in this class, because we haven't learned how to integrate something like this, is use the theorem. Hope that we can use the theorem. So I want to figure out if this function is even or odd. So if it's even, well, let's just put in a negative x here and here. So we do. And negative x to the fourth is the same as x to the fourth. Now the sine function is an odd function. And when we put in a negative x, we get a negative sine of x. So when we put in a negative x, we got back the opposite of our function, x to the fourth sine x. We got back a negative x to the fourth sine x. That means the function is odd. So that means when you integrate the function, because it's odd, over a symmetric interval, it's going to be 0. Okay, class, that is the last of this section, and that's really the last of the new material for this class. So hopefully you can do your 5.5 homework and get ready for the last test. I'll see you later.